Hello, my name is Larry Krusieski. In this presentation, I will be introducing the Green PACE security policy and explaining how it supports secure software development through a DevSecOps approach. This presentation introduces the Green PACE security policy and its role in improving software security. The policy establishes standardized secure development practices across the organization and supports a defense-in-depth strategy by applying security controls at multiple layers. By doing this, it helps reduce vulnerabilities such as buffer overflows, injection attacks, and memory mismanagement. Overall, this policy transitions GreenPace from a traditional DevOps model to a DevSecOps model, where security is integrated throughout the development lifecycle. This matrix categorizes security risks based on likelihood and impact. High-risk areas include memory handling, string safety, and integer operations, which are common sources of vulnerabilities in C and C++ systems. Lower risk areas tend to impact system reliability rather than direct exploitation. This prioritization helps focus mitigation efforts on the most critical vulnerabilities first. To enforce the policy, automation is integrated into the continuous integration and continuous deployment pipeline. Static analysis tools such as Code Sonar, Polyspace, and CPP Check automatically detect vulnerabilities in memory handling, string operations, and integer logic. High severity issues can cause builds to fail, and compiler warnings are treated as errors. This ensures that insecure code is identified and addressed early in the development process. These 10 principles form the foundation of the security policy. Each principle is supported by SEI CERT coding standards as shown. For example, input validation and integer safety are tied to multiple standards, while principles like simplicity and defense in depth guide overall design decisions. Together, these principles ensure that secure practices are consistently applied across development. These coding standards define specific secure programming practices based on SEI CERT guidelines. They address common vulnerability areas such as memory management, string handling, exception handling, and integer operations. By enforcing these standards, the policy helps prevent known classes of software vulnerabilities. Vulnerabilities are ranked based on severity, likelihood, and remediation cost. High priority risks such as memory corruption and integer overflow can lead to system compromise. Medium risks affect stability and reliability, while lower risks tend to impact correctness rather than security. This ranking helps prioritize remediation efforts effectively. This policy defines 3 types of encryption. Encryption at rest protects data stored using strong algorithms like AES 256. Encryption in transit protects data using secure protocols such as TLS to prevent interception. Encryption in use prevents sensitive data during processing using techniques like secure enclaves. Together, these ensure data is protected in all states. The AAA framework includes authentication, authorization, and accounting. Authentication verifies identity before access is granted. Authorization ensures users only access what they are permitted to, following least privilege principle. Accounting tracks user activity for auditing and security monitoring. These controls ensure accountability and prevent unauthorized access. This section focuses on testing for out-of-bounds access, which occurs when invalid indices are used. This type of vulnerability can lead to crashes or unsafe memory behavior. Testing includes both valid operations and invalid access attempts to ensure safe handling of boundary conditions. This test verifies that a single value can be added to an empty vector. This test passed, confirming that the collection updates correctly and behaves as expected. This test validates multiple insertions into the vector. The results confirm consistent behavior and correct size growth. This test ensures that front and back access return the same value when only one element exists. The results confirm correct and consistent access behavior. This test verifies that accessing index 0 on an empty vector throws an exception. The test passed, confirming safe handling of invalid access. This test ensures that an empty vector does not allow access to index 0. The expected exception was thrown, preventing unsafe behavior. These tests demonstrate that both valid and invalid scenarios are handled correctly. All tests passed, confirming that the system safely manages boundary conditions and prevents unsafe memory access. The DevSecOps pipeline integrates security into every phase of deployment, from planning to monitoring. This ensures that security is continuously enforced rather than added at the end. It supports a defense-in-depth strategy through layered security controls. Different tools are applied at each stage of the pipeline. During planning and design, threat modeling identifies risks early. During the build phase, static analysis tools detect vulnerabilities in code. During testing, dynamic testing and fuzzing identify runtime issues. Before deployment, security checks validate configurations. After deployment, monitoring tools such as SIEM systems detect anomalies and support ongoing security. Implementing this policy addresses key vulnerabilities in memory management and data handling. Acting now reduces long-term risk and cost, but introduces short-term overhead such as tooling and training. Delaying implementation increases exposure to security breaches and raises remediation costs. There are still gaps in the policy, including limited runtime monitoring and weak dependency management. Improvements include implementing SIEM tools, enforcing multi-factor authentication, and enabling continuous vulnerability scanning. Real-world breaches, such as the Equifax incident in 2017, demonstrate the importance of these improvements. In conclusion, security must be continuous and integrated throughout development. This policy provides a strong foundation based on SIE CERT standards. By addressing current gaps and adopting additional frameworks such as OWASP and NIST, GreenPace can improve long-term resilience and security posture.